বিহু কেনেকুৱা গ'ল? ভাল গুৱাহাটী গৈছিলে নেকি? এখানে জানাই আজি 18th next chapter start korim aji magnetism. So basically magnetization. তোমালোকৰ ইলেক্ট্ৰিকেল সেইবিলাক হৈছে নেকি? Dipole moment, polarization, electrical polarization, dielectric. So etu similar chapter magnetostatics. So magnetic field, any magnet kenekwa hoy porpora ahe jana ase neki tumalokor? Why there are magnets? Let's say bar magnet amar jibilak ase fridge ot lagay, or even magnetic field of earth. Why I mean, we know why there is a magnetic field, right? First chapter opora. We need moving charges. We need current to get magnetic field. There is no other way, because there are no magnetic poles like North Pole, let's say, or South Pole that will give us magnetic field. It has to be current. Even those permanent bar magnets are because of some sort of currents. Even Earth's magnetic field is due to internal current. So at the core of everything, there are charged particles in motion. So for example, you can imagine an atom like a very simple model, just at a circular current. It's not that simple, like it's not like a planetary orbit. It's orbital, cloud, and all those things. But simplest model you can imagine is like this. Minus E charge moving like this, and this is an orbit. So, but this is not a steady current. We discussed in the last chapter that we need steady current to use it to use in Biot-Savas law and calculate magnetic field. But I discussed that one single charge in motion cannot be steady current, because the charge density is changing. Right? It's here, and then there is something, and it moved, and we have zero charge density. So it cannot be. But you can imagine this motion is so fast that, I mean, at any time if you look at it, it will look like a loop of current. Just like the fan, if the fan moves too fast, then on the average, it's like a flat disk. So in that case, we can approximate this thing as a current loop. And if this is a current loop, then how much is the current? It's charge divided by time, right? dq dt. So the charge is E, and what will be the time? It's distance divided by velocity. The distance is It's r radius, 2 pi r divided by velocity. So minus EV by 2 pi r. That's the current. And for a loop like this, we saw that at a distance, it looks like a dipole, magnetic dipole. Remember that we calculated magnetic field due to a circular loop, and that at far away, its magnetic field looks like magnetic field due to a magnetic dipole, small north and south pole bar magnet. If the distance is z, then the magnetic field was dying like this, 1 over z cube, just like a magnetic dipole. And for such a case, we also saw that the strength of this magnet, M, was current times the area. Right? We found out what is the magnetic field far away, and then we compared that with the magnetic field of a dipole, of a magnetic dipole. And then by comparing, we found that the M term has to be current into area, IA. So in this case, then, for an electron orbiting around the atom, obviously once again the magnetic strength will be IA, right? And so I is minus EV by 2 pi r, and area is pi r squared, right? Yeah. So M will be minus EV by 2 into r, or I can multiply mass, so it will be E by 2m mvr, right? So for this orbit, there will be a corresponding, it will act like a magnetic dipole whose strength will be given by, it's called magnetic moment, minus E by 2m angular momentum. MVR is angular momentum, right? So you can see that if there is a charge in motion, so angular, anything in rotational motion has an angular momentum L. It will have a corresponding magnetic dipole moment. Okay. Now there can be two kinds of motion. আর ওইটা কি মোশন হবো? One is orbital, the other is spin, right? So electron spin is slightly different. Quantum mechanics of gole tomolke gom paba je it's not really like the electron is spinning. It's more like electron spin at a properties, যেনেকুৱা mass থাকে, charge থাকে. Just like that, it has an angular momentum associated. You cannot stop it. Okay, it's like electron is spinning means it can slow down or speed up, or you can stop it. So its angular momentum becomes zero. It's not like that. It always has an angular momentum equal to half h cat cross this value of angular momentum. It always has. It's like its charge. So its charge is minus e. Its mass is some me. And it has a spin. This is a property of the electron that you cannot switch off. Okay? But as it has an angular momentum, it will have a corresponding magnetic moment because it is charged. Charge as angular momentum ase magnetic moment hoboi. Just exactly equal to this, not this number. ইয়াৰ ফ্ৰণ্টত এটা কনষ্টেণ্ট আহে কাৰণ কোৱাণ্টাম মেকানিক্সত গ'লে এইটো হ'ল এটা ক্লাছিকেল ৰিজাল্ট দিছ ইজ ক্লাছিকেল ৰিজাল্ট আৰু মাইক্ৰস্কপিক ৱৰ্ল্ডত কোৱাণ্টাম মেকানিক্স কাম কৰে চ' দিছ ফৰ্মুলা ৰিমেইনছ জাষ্ট তোমাৰ m ইকুৱেল টু মাইনাছ e/2ml ইয়াত ফ্ৰণ্টত এটা কনষ্টেণ্ট আহি যায় that's it. This constant is different for different orbits. For electron spin it is 2, but now you don't need this. We are discussing this just to understand where the magnetic moment comes from. Okay, so imagine like the electron is here and it has a spin angular momentum, an angular momentum which way it points. If the orbit is like this, then it points upwards. Okay, so the spin, if it is up, then it's pointing upward, and because its charge is negative, its magnetic moment will be exactly in the opposite direction, and E is minus C. Okay, so this orbit will have a magnetic moment in the downward direction. Spinor same hobo. Interestingly, so I mean every atom has electrons, right? So there are orbits and there are spins. So in principle everything should be magnetic. We'll come to that. Well, magnetic, why? So everything should be attracting a piece of tin or iron, right? But it does not. Wood, plastic, everything should have magnetic field. কারণ এটা ম্যাগনেটিক মোমেন্ট যদি থাকে it's a magnet, tiny magnet, but everything is made up of mainly electrons. Even a solidity আহে এই ইলেকট্রন বিলাকৰ কাৰণে because they have charge and those charges are negative, and we also have atoms. So when I knock, those electrons in those atoms of the table are repelling this. So basically I cannot pass through. But then they have charge and they have spin or orbits. So there should be magnetic field, but we don't feel it, right? So why don't we feel it? The one reason is any normal temperature, they are directed in all possible direction. So for example, this orbit has a magnetic moment in the downward direction, and even if like this one has a spin, so orbitor karone to eta magnetic moment ase, right? Orbitor karone ase karon ei rotation ase, magnetic moment ase. Even spinor karone aru eta thakibo. We can call this what? ML orbital. We can also call another one ms equal to minus e/2m s, right? Two kinds of. But this atom has a magnetic moment in this direction. A nearby atom is directed like this. So it will enekwa kuri ase, right? Then there is another atom which is exactly opposite. So it's rotating like this. So at room temperature, things are like this. Atoms are in all possible directions, they're vibrating, you know. And so at a magnetic moment, eta atom or a direction of thagile, aru eta atom thakibo, the magnetic momentum of opposite direction. So on the average, at a bulk lole, it's always 0. So that's why we don't see really this phenomena. Ferromagnets are very different. We'll discuss ferromagnets much later. Ferromagnets or at a belak property thake. So that's very different. But there are paramagnets and diamagnets, which are simpler theoretically. Paramagnets are things that are attracted by magnetic field, but magnetic field remove korile, they lose their magnetic property. Okay? Just like, for example, this chalk. It does not attract any other chalk or pen. But imagine if this is paramagnetic, then you bring a huge magnet, it will get attracted slightly, much less compared to iron, let's say, or nickel or cobalt, but it will get attracted a little bit. There are powders, paramagnetic powder and all those things. But if you remove the magnetic field, they are not going to attract anything else, so they lose their magnetic field. And there are diamagnets. Diamagnets, they get repelled by magnetic field. So their magnetic, so you need another, so for example, compass, right? Compass gets attracted to a bar magnet or any other magnet because it itself is a magnet, right? So paramagnetic substance, eta magnet loya hile, for that moment when the magnetic field is around, they also acquire magnetic properties and get attracted. Diamagnets get repelled. So qualitatively, paramagnetism is also easier to understand in terms of spin. Diamagnetism is classically understanding is easier, but exact formula classically is not possible. And it is a completely quantum phenomena. But we'll try to understand this. Okay. See? Exam on? Come on then.
2 দিন
মানে কেতিয়া স্টার্ট হব 6 মে তোমালোকৰ মে মাহত ওকে
স্যার কনস্ট্যান্ট বললে রিভার কনস্ট্যান্ট জি রিভার
কনস্ট্যান্ট জি2 মানে মিনিং বা কি এটো
কনস্ট্যান্ট তো স্যার কি হলো
কি হলো সো এটো এটা এক্সপেরিমেন্টাল ফ্যাক্ট যে ফর এক্সাম্পল ক্লাসিক্যালি এটা কারেন্ট লুপ লৈছো আমি রাইট এটা কারেন্টৰ সার্কুলার কারেন্ট আছে দেন আমি ক্যালকুলেট কৰিছো কিমান ম্যাগনেটিক ফিল্ড হয় উইথ এন ইনস্ট্ৰুমেন্ট and we can see that it is m whole tomar I into area এনেকুৱা right everything is fine এই ফর্মুলা ইউজ করি ক্লাসিক্যালি আমি এই ফর্মুলাটো পাইছো but then এটা অরবিটৰ এটা এটমৰ কাৰণে we know what is its orbit right তাৰ angular momentum orbitor কিমান আছে we know electronৰ mass we know charge we know so this must be the magnetic moment and then আমি measure কৰিছো exactly কিমান হ'ব and we see that এটা factor of 2 missing experiment কৰিলে ইয়াত এটা factor of 2 লাগিব আমি exactly magnetic field measure নকৰো তাৰ effect measure কৰো on the atomic energy spectra যি light ওলাই আহে anyway so তাক এটা factor of 2 যদি আমি ইউজ নকৰো then it doesn't match with the experiment so classically এটো হ'ব লাগে but quantum mechanically এটা g থাকে এটা constant 2 থাকিব লাগিব if we are considering spin orbit consider কৰিলে না লাগে so orbit consider কৰিলে g এই constant to না লাগে but spin consider কৰিলে লাগে so কিয় লাগে এটো explain কৰিব গলে তোমালোকে at least relativistic quantum mechanics লাগিব এটো PAM Dirac okay so at least up to masters তোমালোকে অলপ wait কৰিব লাগিব MSc BSc তো নহয় মানে relativistic quantum mechanics Diracে দিছিল Dirac is a British physicist so তেওঁ equation তো লিখিছিল first তোমালোকৰ Schrödinger equation বুজিব লাগিব এটো probably next sem no তাৰ পিছত fourth sem so Schrödinger equation to hol non relativistic electrodynamics যে কোনো particle কাৰণে আৰু হেতু এই explanation to না আহে spinor so spin আহিলে কি হয় g equal to 2 এটা constant কিয় লাগিব যেতিয়া আমি যাম relativistic quantum mechanics naturally হেতু আহে তা G to 2 হৈ যায় পেয়াৰ কৰে ৰিলেটিভিটি লাগিব ৰিলেটিভিষ্টিক কোৱান্টাম মেকানিক্স লাগিব then you will understand so এতিয়া আমি জাস্ট এইটো ক'ব পাৰো যে এক্সপেৰিমেন্টৰ লগত ম্যাচ কৰাব যদি লগা হয় then এই পাৰ্টৰ লগত ম্যাগনেটিক মোমেন্ট ম্যাচ কৰাব লগা হলে এটা কনস্ট্যান্ট এড কৰিবই লাগে নহলে ফ্যাক্টৰ অফ 2 মিসিং হাফ আহে আমাৰ ৰিজাল্ট যেটো আহিব লাগে তার হাফ আইএস or double IS যেটো আহিব লাগে double IS so the 2 যদি formula use নকৰো that doesn't match but later you will see that G is not exactly 2 2 পৰা অলপ বেছি so সেই কাৰণে G - 2 কৰি G নাম্বাৰটো থাকে সেইটোৰ এক্সপেৰিমেন্ট চলি আছে it's a famous experiment called muon G - 2 experiment my experiment so muon G - 2 experiment is very famous many people did since 1950s and right now it's also going on very important experiment so G2 pura অলপ বেছি কিয় হয় and how much more so hey part 2 হল relativistic quantum mechanics আর 2 পড়া যেটো slight বেশি এই part 2 হল quantum field theory anyway as he said পরীক্ষার চতুর্থ দিন আছে so পরীক্ষার immediately পিছত আহিবা বন্ধ we'll discuss all these things obviously first lecture ot moi ei karone ei fundamental ot time spend koru okay so etia problem hol je everything magnetic even everything paramagnet hobo lage right so okay normal temperature ot randomly oriented hui ase then they cancel out but এটা magnetic field jeti ami if I bring a magnet close to the substance anything wood then ki hobo laga why do we expect that it should be either paramagnetic or diamagnetic what happens when you bring a magnetic field close to a current loop okay so if for simplicity you can consider a loop like this I current আছে I just এইটো এটা square actually square just tilted আছে square to এনেকুৱা okay আৰু magnetic field তুমি এতি apply কৰিছা upward direction তাৰ মাজতে এটা angle আছে theta let's say this is the direction this is theta what happens in that case so for example this is your loop okay this is magnetic field current enekwa goi ase right so current in this direction ot gole dl or direction etu hol right dl I hol এই direction ot so তোমার force or direction কি hobo dl cross b কারণ force যেটো আছিল on a loop it was steady current I dl cross b this Lorentz force or pora exactly etui ahibo q v cross b use korile this will be the formula you should remember this so dl cross b hol amar force or so this is our loop this is the direction of current now this is the magnetic field dl is towards you b is in this direction okay so dl cross b dl cross upward b well this will be the direction of force so a part of loop will be pulled toward this direction so if this is pulled in this direction dl to yata hi opposite hoi goise right so it should be pulled in that direction yat jodi force enekwa hoy yat outward hobo lagibo and dl change hoise force so change hobo so it's like it's trying to do this and that force will be equal and opposite right so tar mane eta torque apply hobo ei direction or duta useless and ei direction of tomar eta force thakibo outward iaro thakibo outward duta just pull kori zero hoi jabo right there is nothing to do. It's just pulling these two in this direction, gets cancelled out. Here to force to cancel, of course, total force kiman 0, but torque is not 0. Okay? Okay, so for simplicity, this is the length and this is the length. So L and L. Force will be simply I dl or integration kiman L into B, right? I can say, let's say the direction is X, Y, and upward Z. So, enekwa thakile Y direction of eta thakibo for this part, positive Y, aru eta thakibo say A, B, C, D. So, CD karone etu thakibo, AB karone minus ILB Y plus these two, right? Okay. So for these two, these are, what are they? They constitute a couple of force. Couple of forcer karone torque kiman hoy? One of the forces and the distance between the two. Or just simply total torque calculate korile hol. Torque keneko calculate korim? R cross F.
Force into perpendicular distance.
Not just in, oh yes. Force into perpendicular distance. Aru perpendicular distance keneko ahe? Sin theta. R sin theta. Hey karone you can say R cross F. So R is this, which is L by 2 cross F. So basically tomar our direction to keneko hobo. So force in this direction, R in this direction, R cross F into the page. So we can just write the magnitude. Also etar karone distance R kiman L by 2. But then R eta torque ase. There is also down in this direction because A2 apine kurai ase. This is trying to turn in this way. Both are trying in the same way. So basically same torque. So twice বুঝি পাইছো না? Distance whole L by 2 and force whole I L B and the direction will be minus I think yeah, force in this direction, R in this direction, R cross F inward, yes. This is it. So basically I L square B. And of course there is, so if this is cross, then there is sin theta. Sin theta ase, right? Or IL square B sin theta minus x. L square is what? Area of the loop. So tau is IAB sin theta minus x cap, and IA is M. So MB sin theta minus x cap, or simply M cross B. So tau is M cross B. Okay. So that means there are atoms in nature and there are orbits. So electron is orbiting. And if you bring a magnetic field B, if you apply a magnetic field B, there will be a torque applied on them. magnetic field eta apply korile torque applied hobo. And what does the torque do? It will try to align the loop along the magnetic field, right? So electron eta orbital or karone eta magnetic moment ase. So it's a magnetic dipole, right? It's like a magnetic dipole. If you apply magnetic field, the field will try to align this because there will be a torque given by m cross b. And this torque will try to rotate the electron's orbit along the magnetic field. And therefore, tomar ei je random যেটো arrangement আছিল atom bilak randomly আছে এটা এনেকুৱা ঘূৰি আছে এটা এনেকুৱা ঘূৰি আছে এটা এনেকুৱা randomly ঘূৰি আছে. But then you apply a magnetic field, each one of them will try to align along the magnetic field. কারণ torque এটা apply হৈ যাব, right? আগতে b0 আছিল, so m could be in any direction. Now there is a b, that b এর কারণে torque applied হ'ব, they will all try to align. Okay, and that's why kote mane ei material to lole that every atom in it will try to align along the magnetic field. But still temperature high ase, so vibration or karone perfect alignment no hobo, but partially hobo. Partially jodi hoy, it will have tiny dipoles roughly upward, and that means there will be a magnetic field due to these dipoles. Okay, now this turns out যে তোমার এটু mainly spinor karone hoy, orbitalor karone nohoy, because it's easier to rotate a spin. Kon magnetic field ki kori ache, it's basically applying a torque m cross b, so torque will try to rotate these, but it's harder to rotate the orbit compared to just the spin. Again, easier to understand. Eta rotate korar karone tomar torque lage, right? To rotate something you need torque, and something just like to move something you need force. To accelerate something you need force. If something is more massive, you need more force, right? Mass beshi hole force beshi lage to produce the same acceleration. Similarly, moment of inertia beshi thakile you need more torque to generate rotation. Moment of inertia is like mass in rotational motion, so you need more torque to rotate something that has more moment of inertia. Now electron at a spin, just let's say it's spinning, okay, this has mass m, but the same electron is orbiting, same mass m, but in this case the r is much larger, so mr square of this system is bigger. So this orbital system has more moment of inertia, and therefore rotating it is not easy. It needs more torque, but this spin on its own axis has much less moment of inertia, right? Etu to bujhi paise, mass to same ase, distance bela komi goise, so etu moment of inertia much less, so much less torque holeo you can rotate it. And therefore, the most of paramagnetism that we see is due to the spins of this. So, not the orbital part, but due to the spin part. Spinor karone hetu ahe, not because of the the orbits. Now, why don't we see then paramagnetism in everything? So agote, okay, first we understood that randomly oriented ase, so that's why there is no magnetism. But magnetic field apply korile there will be an alignment, and we should see. But no, there are only few paramagnetic substance, not only few but limited some, not everything, right? So why? Because once again, Pauli's exclusion principle, Pauli's exclusion principle. So every orbital, let's say every orbital in chemistry, even quantum mechanics na paleo chemistry paisa. Orbital eta Pauli's exclusion principle or karne, there is an up spin and there is a down spin, right? And that's why they cancel out each other. So total spin 0 hoye jay a system tour. And if the total spin is 0 of a system, then S to 0. So is system or after all magnetic moment to 0. So magnetic field apply kore labh nai. And that's why only in atoms where there are odd number of electrons. Odd number of electron hole ki hobo? Match kore last of jetu ase outermost tat eta electron thaki jabo. And that is unpaired. So heitur karone tomar magnetic moment eta thakibo, and that will give rise to your paramagnetism. Okay? Aru jibilakor even number of electrons, there this part is 0, but this part then orbital to tougher holeo all of the affected hobo, jitu really negligible in general. And tomar ei outermost electron or karone jitu unpaired tar karone mostly paramagnetism dekhai thakbe. So if it is odd number, paramagnetism is much larger karon we can rotate the spin easily. So there is this part, orbital part is always there. Karon orbit to ase, orbital angular momentum ase. Okay, দুটা ইলেকট্রন আছে, two charge are in orbit, so orbital angular momentum আছে, তার কারণে এটা ম্যাগনেটিক মোমেন্ট থাকিবই, but they are randomly directed. Now you apply a magnetic field, but it's harder to rotate the orbit, but there will be slight either rotation or another effect we'll discuss. But the thing is, it gets shadowed by the spin part. And he too easier to rotate, so spin or karone magnetism to besi hoy. So if there is like odd number of electrons, tetia hetur magnetic field iman beshi hobo je orbitor karone jitu slight ahe that gets neglected. But jetia spin to nai, just even number ase, and this part is 0, a negligible holeo tetia eitu important hoy jay. And this part turns out to be orbital karone is kind of opposite. So it attracted no hoy, it always opposite hoy. Mane magnetic field z direction I apply kori, tar opposite direction of magnetization produce hoy. Ekane repulsion hoy. So repulsion is a natural nature of every atom. Every atom are ase, but it is so less that we cannot really measure it well. So jikono bostur ase etu, and etu orbitor karone ase, so it is there. Odd or even number of electrons, it is there. Even hole this dominates, odd hole this gets neglected. Okay, so this is universal, and it is called diamagnetism, the one due to the orbit, and that is the one due to the spin is called paramagnetism. So qualitatively, to understand diamagnetism, once again this model will be useful. Eta electron orbital minus E as a charge, R as a radius. So velocity direction, of course, in this direction. Now, in this kind of situation, tomar a rotational motion too, basically due to electrostatic attraction. Middle eta proton ase, right? Let's consider hydrogen. Then middle nucleus eta thakibo. Iate electron ase. Hey attraction or karone eto ghuri ase, right? So centripetal force etu ase tomar. Ei electrostatic attraction or karone centripetal force to ahe. So 1/4 pi epsilon naught E into E, Q1, Q2, E square by R, just magnitude to likhi, so R square. Etu hol attractive force, right? Etu amar ki dibo square by r must be this, then we'll get an orbit of radius r. Simple. When there is no magnetic field applied. Now magnetic field apply korile ki hobo? What will have the impact on this? Era impact holo ke, let's say eta magnetic field B apply koriso in this direction. Then at this point, let's say the V is directed in this way, right? So V cross B, so your force is what? Q V cross B. V in this direction, B is in this direction, V cross B is outward, but then your charge is minus E, so that flips the direction. So your force is in this direction. So force এই direction হলে then আমার electrostatic force inward or logot আৰু এটা force এটি আহি গৈছে, right, which is magnetic force. So এতিয়া আমার this plus magnetic force equal to mv square by r হ'ব. But then this V অলপ different হ'ব, কারণ attractive force যদি বাড়ে সেইটো cancel কৰাৰ কাৰণে it should move faster, right? It should move faster. So now the next equation will be what? This was there, so this will be there. 1 by 4 pi epsilon naught E square by R square plus 8 force ahibo E VB minus lekhana ekhon everything is inward. This is inward, this is inward, EVB, right? Now I'll write it as V prime. On etia velocity to belek faster equal to m V prime square by R. And now this is the equation. In presence of magnetic field, this is the equation. But this part is same, right? So I can replace this here. So 1 over 4 pi epsilon naught E square by R square is just mv square by R. Agor jitu velocity asil. Okay? And that means E V prime B equal to m by R V prime square minus V square, or m by R V prime V prime plus V into V prime minus V, yet E V prime B. Okay? We are considering really a slight magnetic field, like not a huge ultra magnet. Okay? Our bar magnet or magnetic field due to Earth. So this is a weak magnetic field. In that case, we expect this force to be weak. And so the change in velocity is also slight. In that case, V prime and V is almost like the same. So we can put V prime equal to V. But not here, then everything becomes zero and useless, right? So difference to tiny. Tiny difference, we are trying to calculate the tiny difference. But sum korile, we can replace, we can approximate. So let's say V prime minus V is some del V, and this is very small. So this is del V. And yet ami V prime equal to V put kori dim, yet V prime equal to V put kori. Then what will happen is EVB equal to m over R 2V, right, into del V. 2V V del V. VV kati jabo. Let's write it here. What we'll get? Change in velocity equal to EBR by 2m. No, EBR by 2m. Yeah. Okay. So this is the change in velocity. And this is positive. And speed up hobo. and this change in V এর কারণে there will be a change in angular momentum, right? So V যদি একটু চেঞ্জ হয়, L কি mvr, so there will be a change in L due to this change in V, right? So M EBR by 2M R EBR square by 2. Okay, this will be delta L, and that means L or change or karone M or eta change hobo magnetization. So del M will become, so let's say minus E by 2M EB R square by 2, right? Okay. I bet a video interesting. So now the interesting thing to look here is this. Velocity yet increase hoise, but still magnetic field to apply korar karone the changes ahise, velocity data change ahise, tar karone angular momentum ot eta change ahise, as a result magnetization or eta change ahise, but it's in opposite direction. So magnetic field z direction ot apply kore তার অপোজিট ডিরেকশনও ম্যাগনেটাইজেশন প্রডিউস হবো or change in magnetic moment. So which means there will be repulsion. Now someone can say that okay ইয়াত রোটেশন তো আপনি clockwise লইছেন, এই কারণে এইটু হইছে, রোটেশন যদি কাউন্টার clockwise হয়, or if I apply the magnetic field in this direction, then what? Let's say it was like this. Now obviously force to outward hobo, right? Force eti outward hobo. If force is outward, tar mane inward force komibo, right? Agote jetu electrostatic force asil etu olop cancel hobo, so that means inward attraction to komibo, and if that happens it will slow down. Agote speed up hoise etia slow down hobo, but slow down hole ki hobo, effectively current to kome jabo na. I is after all charged by time, slow hole time to baribo, so E by 2 komibo, so less current. If less current, then less magnetization, so magnetic field apply korisu tar magnetization komi goise, so it's again an opposite phenomena. So the thing is, orbitor karone z magnetization produce hoy, it's in the opposite direction, and therefore it will be repelled. So it will be repelled. So ki hoy je kono eta material or osorot magnetic field eta loi ahile or magnet anile, it always has two effects, one due to the spin, the other due to the orbit. If the electrons in that material are even in number, then they all pair up and cancel out. Only remaining thing is the orbit. Orbitor karone repulsion hobo, so that material will show diamagnetism. Okay, now this is important to remember. 1 mark, 2 mark, I don't know question is that which materials will show diamagnetism. The next thing is, if electrons are not paired up, so if there are odd number of electrons, then still this orbital repulsion will be there, but it's much less compared to the attraction due to the spin part. So the paramagnetism will dominate. If the number of electrons are odd, paramagnetism will dominate. If the number of electrons are even, diamagnetism will dominate. Okay, and diamagnetism is always there in everything, even if it doesn't dominate, it's there. Okay, paramagnetism is not there always. Ferromagnetism is much complicated phenomena, so that is for later. Ferromagnetism hol magnetic field remove korileo thaki jay, right? Era iron or piece magnetor logai rakhile all of time, next it will remove kore anile, that becomes a magnet. You probably have noticed iron becomes a magnet. চ' সেই যে এলাইন হৈছিল বেচিকেলি এলাইনমেণ্টবিলাক থাকি যায় they don't flip. The phenomena is much like the birds flying actually flockত ফ্ৰণ্টত এটা বাৰ্ড ফ্লাই কৰি থাকে যেটা মিম আছে যে চ' where are we going পিছৰ বাৰ্ডে পিছৰ এইবিলাকে চৰাইয়ে where are we going ফ্ৰণ্টৰ ওৱানে সুধি থাকে where are we going পিছপিনে যিটো আছে we are following you. So they just follow each other actually, and as a result they become this huge. So এটাই তাৰ ওচৰত যে তিনিটা আছে ফ্ৰণ্টত আৰু এই দুটাত ফলো কৰি থাকে অলৱেজ. So they are moving in this direction সেই দুটা মিলি এটা গোটেই ফ্লক যিটো আছে তাৰ এটা ডিৰেকশ্যন আহি যায় সেইকাৰণে যে বহুত ইণ্টাৰেষ্টিং ফেনমেনা আছে বাৰ্ডৰ ক্লাউডৰ নিচিনা যে এনেকুৱা মুভ কৰে একেলগতে কেনে মুভ মানে কি কেনেকুৱা ইয়াত এই পাৰ্টত এটা বাৰ্ড আছে সেই এণ্ডত এটা আছে how does this bird know that this bird will do this particular movement then মিলি এনেকুৱা যে এটা synchronized dance কৰে এইটো ৰেণ্ডম নহয় এটা আৰু এটাৰ লগত এনেকুৱা লাগি নাযায় actually so why this nice movement so it has a very strong connection with ferromagnetism.